Well, I want to thank Steve for inviting me to be here. It's better to be seen than viewed. And I had the unfortunate accident last November where I was T-boned in my truck. The driver hit me doing about 70. Driver's side T-bone. And my doctor says, we don't usually find many people who survive that. So I appreciate the opportunity. I want to talk to you a little bit about what we've learned about grouts. This presentation has a lot of embedded video. So more video, less me. You're going to be really interested in that.
We have a problem there because we didn't realize there was video.
Okay, well then I'll have to do a song and dance now. Then it'll become a story. A story either starts out like Once Upon a Time or This Ain't No BS. One of the two.
I'm sorry.
Oh, that's okay, Steve. We did a grout study back in 1999, went to 2006, and the reason we did a grout study is we were seeing our ag contaminants go up like that hockey stick curve, No matter what we would do with our regulations or our requirements, we kept seeing a climbing of that contaminant. So what the grout study did, it revealed things that grouts don't perform like you think they do. And they don't perform like the industry always thought they did. We know that cements will crack. There's two types of cements, cement that's cracked and cement that's going to crack. We also found out that cement does not bond real well to PVC pipe. In fact, during the heat of hydration, it pulls away and you got a little itty-bitty microannulus there. And if you could see the videos, it would really show you a great example of that. But
We're gonna try it.
We're going to try it?
Try it.
All right. I got faith in you guys. You're from the Big Ten. I know you can do it.
Don't like me to try to tell them.
So what we've really come up with is it's not an answer of cements versus bentonites. It's really an answer of where you put your grout and what that material is made of. So if you're in a real porous area, say like for an example I always give is if you got a real good perk rate in a septic system, you don't want to put a high water slurry there because that soil is going to pull the water out of the bentonite and you're going to have fractures. So that maybe cement's better there. But if you got a good knowledge of that subsurface, then you're going to have a pretty successful result in protecting your wells. Now, after the grout study, went around the country and talked about this, and they said, well, what are you going to do about all those wells that were already in before you guys got smart and did your study? Well, we've come up with a method that we're actually looking at irrigation, because irrigation in our end of the country is big. We've got over 99,000 irrigation wells in Nebraska in 93 counties. So you can't hardly go outside and trip over an irrigation well somewhere. This produces about 92 billion gallons of water to our ag community. So if we're ever going to fix our problem, let's start with those big producers first. As you can see, our biggest challenge is we have a lot of wells that were put in before we had construction standards. And then those construction standards may not have been adequate at that time either, what we've learned from the grout study. So really, in all practicality, anything that was installed before 2014, when we revised our regs, those wells are vulnerable. They're vulnerable to contamination either from the surface or from commingling in the borehole. Can you get this to work? Yeah, okay, cool. This is our well model in her fish tank. Okay, what she's going to show you is, it's a demonstration, an illustration of how wells that are properly constructed can be contaminated by wells that were constructed before we had standards. And what's in that fish tank are 4 simulated wells. One is all gravel packed to the surface, which we have done that since basically 1988 backwards. The next well to it is a public water supply well that shows full-length bentonite grout, and that black stripe through the middle of that fish tank is to illustrate a confining layer. Okay, she quit talking. What this, and you can Google this, just go to the Nebraska, just Google Nebraska Water Well Standards and find the well model, and it'll play for you. But what it illustrates is how fast contaminant goes down that borehole on the gravel-packed well. And if you think about it, gravel pack's designed to do what? It's designed to carry water in a rapid manner. It doesn't know it's supposed to be horizontal. It'll also do it vertically. So I urge you to go look at this illustration. The impacts we found are the well construction in our state was all based on water quantity. Get as much water in the well as possible to pump out for that producer. In 2014, we changed that to look for water quality. How can we separate those aquifers and those different levels? We also found out that by doing that, we protect the infrastructure of our irrigators. We get rid of some of this iron, manganese, the wear and tear on pumps and systems. And a typical center pivot system is around 60, 70 grand with another 50 in the well. So you're looking at a substantial bit of coin to be putting vulnerable there. Now the poorly constructed well. So I'm gonna say this tongue in cheek because this is what we did before 1988. Every well was gravel packed to the surface. We hope there wasn't an open annulus, okay? That was the best technology at the time. And then in 1988, we said, you gotta put a surface seal here. So we put a surface seal in the top 10 feet, try to keep all the contaminant from the surface coming down the borehole. The Grout Study showed us that it wasn't adequate. So, and especially in areas where we had perch water tables. And we do have that a lot in eastern Nebraska. And I imagine you do here in Illinois as well. A lot of perch tables. Those commingling of those different water qualities can really mess up your aquifer. What you're looking at here in the still, this is a picture of an irrigation well where we saw a perch water flowing through the crack of a tile. And this water was flowing probably 20 gallons a minute. Okay, the tile above the leak, you see nothing. It's nice and clean. The tile below it is full of manganese, and that's coming from that perched water zone. It's also where all our nitrates were at. That's what it looked like before we cleaned it up. Oh, you can barely see that water leaking through there. Well, now after brushing, you can see how freely that water's flowing. That's going from a perch zone that was at 20 feet below the surface down into a base aquifer that was 216 feet below the surface. That irrigation well, the nitrates were about 10.4 when we started working on it. There it is, 10.5. After we cleaned it and brushed it and we were airlifting it, we did a grab sample down in the production zone where we found that the base nitrates were like 0.6. So they gave us a hint, there's a communication here. It's not just a communication in the borehole, it was also communication through the casing. So, but it's easy to seal the casing. You could line it, you could choke it off, but you haven't done anything with the pathway on the outside where that gravel pack is carrying it 24/7, 20 gallons a minute, because they have different hydraulic gradients. So our challenge was, how do we go in there and do a retrofit design and not destroy the producer's irrigation well? And the bigger challenge is, how do you convince a producer to let you try this on his irrigation well? You guys think it'll work, but if you ruin it, who pays for it? So A lot of times we found wells that they replaced and they haven't decommissioned yet, and we were able to do our study on that. This is kind of a design we came up with. There was two ways we decided to study this. We were either going to drive injection pipes into the annulus and grout it from there. And if it was pretty shallow, we felt we could do that. Or if it was deep enough, we were going to go down, we were going to perforate the casing and put inflatable packers around that perforation and actually pump grout into the borehole. We were really new at this, and you know, whenever we get started on a study, we have a talent of finding out projects that nobody's ever done before. So we kind of have to learn on it as we go. One of the big things we learned that's critical is knowing what's just exactly what the subsurface consists of. Now I want to show you a driller's log that's on the right-hand side. And this driller was really trying to be very cognizant and intent of what he was looking at. And then we ran an E-log, same driller, we ran an E-log in that same borehole. Well, you can see that we found about a 2 or 3 foot clay layer around that 50, between that 50 and 60 foot mark that he don't see in his drilling log. And it turned out in that project that was key, because if we had not found that, we wouldn't have been able to seal it off. And what we do is we go in and we delineate a site. We drill segregated monitoring wells deep in the aquifer, shallow and intermediate, and we E-log every one of them. And this is an example of one perforation tool. It was actually a saw that we could put inside of a 16-inch PVC well and cut slots. But if it got any smaller, actually, if it was 16 inches or smaller, we'd actually end up cutting the well in half. So we had to come up with another device which actually just drills holes to perforate it. But it can be done. Now these are the drilled holes in a project up at Laurel, and you can see that we didn't impact the well. We didn't really bother too much, and we were able to go around on the compass circle and get one on the north, east, south, and west side of the well. And those are about 5/8 inch holes. And this is actually looking at the vent hole as they're grouting the well. So you're actually seeing the commingling of the bentonite fluid coming up to that level 5 feet above where perforation takes place. And we got that annulus sealed off. I'm kind of an old rocker, that's why I put smoke in the water, you know. Da, 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 da. This is going to show you the impact from the injection pipes where we were cementing shallow. And you see the grout showing up on the left-hand side of the screen. Now you'll watch it. It'll go around our clear sight tubes, and it'll end up clear on the right-hand side. So that's exactly what we wanted to do. We wanted to fill the voids of those pathways where a contaminant can come down from the surface. Most of all the success of this was the ability to use clear PVC casing, either in sight glasses or in research wells, things like that, where we could get good pictures of actually what we were able to do. So now you see how we cemented that up. This is another good one. This is where you're going to actually see the cement grout traveling through existing gravel pack. And this is in that well I showed you to begin with where the nitrates were so high. Kind of looks, you'll see it displacing water. It flows pretty easily. And really all we're trying to do is take advantage of what's already in the borehole, that big aggregate, and we're just trying to seal off the porosity in that big aggregate. This pump's really easy. The the pressure on the grout pump was like 65, 70 pounds of pressure. So we're not in danger of fracturing casing or doing any hydrofracking in the formation. It's pretty low impact as far as that's concerned. Our verification, we had a shallow well up at Cedar Bluffs when we actually did the pump test after we did the seals. And you see the curve actually raised during the pump test rather than drop. Well, it raised just in accordance with the atmospheric pressure. We had low pressure come in. It was nasty that day. And you can see it reflecting on the data loggers. But you can see on the pump curve, on the 24-hour pump test, you can see where we ran out of gas about midnight, and the curve spiked up again. Then it took us about an hour to get gas back in the generator. Our base aquifer we saw drop down, but we never saw anything drop down in the perched aquifer. So we know our seals held. So at that time, we started off on our 24-hour pump test. The nitrates, after we sealed it, was at 0.417, and then at the end of 24 hours, it was non-detect. So we actually removed 10.4 parts nitrates from that irrigation well. But also, we had manganese up in 13,000 parts per billion. Yeah, that removed it back down to 78. So you see there's different water quality issues other than just contaminants. This little town of Laurel up in northeast Nebraska was a real mess. They ended up having 5 wells, but only 2 of them were registered that they knew where they were at, and only 2 of them were active. The well in 2009 was created with that full-length grout, like I wanted to show you in that model. And the selenium in that well was only at 18 parts per billion. Their town wells that were fully gravel packed in the bottoms were upwards of 60 parts per billion. So I knew there was a good chance that we could succeed here if we could just replicate what they did with the newly installed public water supply well. We ended up talking to the old water operator whose name was Ole, and Ole knew where the old well was, and the old well happened to be about 40 feet from where our project well was. And this well was drilled in 1955, and you can see that's the annulus. If you can see that little brown ring outside the casing, that's how much borehole they had. It was a cable-tooled well where they just drove it in the ground. When we uncovered this thing, it had been decommissioned properly at the time, filled with gravel and cement cap put on it. We took the cement cap off, brought in a vac truck, removed the gravel, and it worked until we got to the hole in the casing, about 40 foot deep. We sampled that water, and that was 178 parts per billion for selenium. So we went ahead and we perforated this well, grouted it, sealed it up. And then about 10 days after we decommissioned our that well, that old 55 well, the project well went from 101 parts per billion down to 43. We got the project well back in compliance just by decommissioning the smoking gun, to say the least. So this new design of rehabbing wells, the real gold here, the real value is going to be in decommissioning old wells. Because what that model would have shown you is even in a decommissioned well where you fill the middle up with bentonite, it travels down the gravel pack like a superhighway. So by going in and decommissioning the old wells that nobody uses, nobody cares about, you're going to improve the water quality chances tremendously, especially in these small towns. This chart, basically I'm going to run through it quick. 84-1A is our project well. Its initial selenium was at 76 parts per billion. After we decommissioned the old 55 well, it went to 33, and then we decommissioned another well that was in the same pump house It went back down to 16, which is right in line with what their new well on the hill did. So we feel real good about this. This town is now off of administrative orders, and they've gone back to sampling once a year every 3 years. They saved themselves about $1.2 million rather than to have treatment or doing a blending project. So what's needed, and it's the same thing as I said when we did the grout study, you got to understand what the whole borehole dynamic is. You got to know where the soils are at. You got to know what every change is. The best log you can get may even miss a few things. That's why I'm a big advocate of e-logging and knowing what that e-log does. Geoprobe was a great tool in this project. Core sampling is another great tool. You don't miss a whole lot between a geoprobe, core sample, and an e-log. And once again, once you have identified where those potential aquatards are at or those differences in the aquifer, you can go in and place your sealing materials there and reestablish that filtration system that Mother Nature laid down for us. You know, a lot of times we've hurt ourselves by going in and compromising that filtration system and not understanding it, not replacing it. And if we can do that, the grout, if we can put a good dynamic seal in there, we're going to have a lot better chance of improving our groundwater qualities. So with that, I would take any questions.
One of the things we've been working with, like Baroid and Wyoben with, is that the water chemistry in the well really affects well abandonment. Their products are rated, and as the products move forward very quickly, some of them aren't a good application for abandonment if the hardness or the chlorides are really hard in the well. They're specific products. So I think that's something you have to keep in mind is as the technology, like with Baroid and Wyoben, changes, you need to be familiar not only with the things you said, but with the water chemistry.
Well, absolutely. You know, we learned that in the grout study. And when I started out earlier, I said some places bentonites are good, other places cements are good.
Yes.
You may end up even with a composite seal.
And I work with the drillers in Michigan, and they're really becoming much more savvy working with the salesmen from these products about which the proper application is. So it makes a huge difference.
Oh, yeah. Well, thank you for that comment.
I was wondering how your regulations have changed now that the study has been implemented.
Oh, our regulations, basically we've got full-length protection in the borehole now. We treat all wells the same. We used to have a potable standard and a non-potable standard, which was really kind of silly because it's all coming out of the same source. So the public standard of a full-length chip grout seal, we needed to replicate that in a practical manner. So we now feature a primary seal, which is either placed on right above the screen area or the first clay layer above that production zone, or for those areas of the state that don't have either one, we put it at the static water level. So it's like a water stop. And then in between, because we know gravel pack flows so easily, we require either a grout component in that you can mix with sand or gravel to kind of hold the cost down. Or you can full-length chip it if you want to. We don't prohibit that. Or we don't prohibit using a sand cement, which we know bonds better to PVC than just neat cement. And then at the top of the well, we've increased our surface seal. So basically, if any contaminant flows in and contacts the borehole, that borehole material is less permeable than what's around it. So it kind of diverts it back to that filtration system. Before we didn't do that. We just had a surface seal at the 10-foot level. And we were really floating along thinking that was a good idea. And it was, but it wasn't enough of a good idea.
Did you find that chips worked the best?
Oh, yes. In our grout study.
Even above bentonite slurry and cement?
Yeah, one of the big myths of the grout study the grout study exploded was that bentonites don't always rehydrate, especially water slurries. Once they crack, they crack. They won't come back. But one of the nice things that we proved was the chip seals will crack, but they will rehydrate. We saw that continually happen over an 8-year period in one of our sites. So that's why we kind of hang our hat on it. If there is a default, it's chip bentonite, but it also, like the lady said, you have to be cognizant if you're putting it in a high salt formation or if you're putting it with a high chlorides, that's probably not best either. So you got to understand that.
And did you do any study on the size of the annular space?
We did. We used geoprobe to see if a small annular space would help, and it didn't. And we used, in our geothermal systems, we were drilling 14-inch boreholes to put in 3/4-inch loops, which nobody would ever do, because that's crazy, but we had to get 2-inch sight glasses and everything in there, and it didn't matter. The size of the hole didn't matter, it's what you put in the hole that mattered.
So the size of the annular space didn't matter?
No.
Okay, thank you.
It didn't really make much difference. But one caveat is, though, you got to have a big enough annular space to place the chips. They've got to be able to free fall and not bridge.
And those are natural chips, not the preformed.
Right, right.
And that was really the message that I was hoping would get across, is that natural chips are the best thing to use for grout.
And they are. They hydrate, they rehydrate, they don't give you any bleed off, so.
Yep. Any other questions? All right, so I promise when we come back at 1:15, it will not be as cold in here. So I'm gonna go find out what's going on, because I'm cold too. Let's meet at 1:15. You've got your lunch menu thing where everything's at. There's a lot of places close by. If you have any other questions, let one of us know. Jennifer and Katie are back there. Yuki's right here. Thank you for your time.